Okay, let's get started. Today we discuss fixed point theorems. We could hardly overstate the importance, the significance of fixed point theorems. Uh, we meet them everywhere in modern, in dynamic economics. Just to mention a few scattered examples from the close end, when we study the stability properties of a difference equation, we use a fixed point theorem. To be more specific, when we iterate on the Bellman operator in the hope of finding a unique um, value function that solves the Bellman equation, we also use a fixed point theorem. So the success of the iteration on the Bellman operator stems from a fixed point theorem. Or to be more specific, even more specific, the strategy to solve Lucas' famous paper entitled Expectations and the Neutrality of Money is also built on a fixed point theorem. So fixed point theorems come in various forms, but at the end of the day, we have a general form, we have a general scheme that describes all the fixed point theorems. We have a set in a vector space that can be a whole space or its subset. We will specify it later. There is a mapping on this set, and a fixed point is a specific point in this set by which we claim that the mapping gives the same point. So if we substitute this fixed point into the operator, we receive the same point. So actually the iteration stops at this point. We will see that different results specify what is necessary for the existence and the uniqueness of a fixed point. So in various settings, we will study the conditions under which we can be sure that a fixed point exists and the fixed point is unique. So this is one point we will cover today. So we can prove the existence and the uniqueness of a fixed point, but we can do more. Even if we know that there is a fixed point and the fixed point is unique, it is a different, related but different thing to be able to find this fixed point. As we will see, there are algorithms, iterative processes that are available to find the fixed points. So in this case, we will transform the mapping into an operator. So the mapping becomes an operator, and we will take successive steps to generate further and further points. So it becomes an iteration, and hopefully under specific conditions, when iterating on the operator, we will gradually approach the fixed point. And it comes from the very nature of the fixed point. If we find the fixed point, we will never leave it. So hopefully we can find conditions under which the successive steps taken with the operator will lead us to a fixed point. So what we are going to do is to set up convergence processes. So in one way or another, we need to measure the distance between the successive steps. So at the far end, when we have reached the fixed point, the distance between the points of the successive steps is 0. But initially, when we start the iteration, we have no idea of the nature of the fixed point. So generally, we need to be able to start from any point in the set, and by starting in any point of the set, the whole space, for instance, we must be able to find the fixed point eventually. So what we are going to do is to study the conditions under which this convergence process proves to be successful. So when we start the iteration, the distance between the initial point and the fixed point, of which we know the existence and uniqueness at best, so we don't know where it is. The distance between the initial point and the fixed point is definitely not zero. And in the successive steps, we will generate points in the set, and hopefully the distance is decreasing in the successive steps. Finally, it tends to zero, so finally we will find the fixed point. So over and above the set, the vector space, and the mapping, we need an additional thing, a metric by which we can measure the distance between the successive points of the iteration. So we need a space or a set in this space. We need a mapping of which we create an operator, and we need a metric by which we can measure the distance between the successive points. So this is all we need. First, before digging deep, we will see that if a point is a fixed point of a mapping, then it is also a fixed point of the operator, which is the rth power of t. So as a first result, let's see this claim. What we want to show is not too difficult. The claim is the following. If x asterisk is the fixed point of the mapping, then, according to the claim, the same fixed point is the fixed point of the rth power of the same mapping. To start, before starting the proof, which is very quick, it may be worthwhile to spend a split second on explaining what the rth power of a mapping is. So, in general, it means this operation. Yep, it's enough. So we can decompose, the rth power of the operator. So this is the claim. And this is what we want to prove. All right, so we have this operation by claiming that this is the fixed point of the operator t. If we decompose this operation into two operations, we receive this expression in which we know that this is the fixed point because of the assumption. X asterisk is the fixed point of the operator. So we can take a step, right? And in the next step, we decompose again. and this is the fixed point again. So we do this in successive steps, in finite steps, and in the end we will receive this phase we use again the fact that the point is a fixed point, and we are approaching the finish line. We are decomposing again. Then this is the final step, and by claim, by assumption, this is the fixed point. So finally we demonstrated that the fixed point of the operator t is also the fixed point of the r's power of the same operator. So as you can see, the proof is not too demanding. Before going on, we need additional definitions. We have a metric space, so a space and a metric on this space. We have a mapping on this space, and the mapping is said to be Lipschitz if for some non-negative alpha this inequality holds. What does it mean? It's easy to realize that this condition, the Lipschitz condition, is very loose. On the right of this inequality, we see the distance between 2 points in the space before applying the mapping to them. And on the left, we see the distance between 2 points which we receive by applying the mapping to the points. And actually, this inequality compares the distance before and after the application of the mapping to the points. Depending on the value of the parameter alpha, the distance before and after may be very different. So given that alpha may be any finite positive number, the distance may even be increasing. So after applying, by which I mean that after applying the mapping to the points, the distance may increase. This is not too good a property, because by applying such a mapping in successive steps, we can see that the distance may even increase, and we could hardly find a fixed point if we had a Lipschitz mapping. So this mapping may even be expansive, by which we mean that the distance is increasing. So we need to add additional restrictions to rule out this option, this possibility. So we can add additional restrictions on the parameter alpha. So in the next step, we can rule out the expansive case. So we restrict alpha to be 1, and in this case we have the next form of the inequality. In this case, we can say that we could get rid of the possibility of expansion. So the distance might be the same, or the distance might be decreasing. We cannot know for sure if the distance is actually decreasing, but we can know it for sure that the distance cannot be increasing, so we could rule out the expansive case. So what we have now in the next step is a non-expansive mapping. In the next step, we require strict inequality, but alpha is still 1. This is a contractive mapping, by which we mean that the distance is decreasing. So by applying the mapping in successive steps, the distance must be decreasing. This is good because we actually have the hope of finding a fixed point if there is any. But we can still add further restrictions. If alpha is strictly less than 1, then we can restrict the rate. We can place a restriction on the rate of decrease. So as compared to the case of contractive mappings, in the final step, the contraction mapping, in the contraction mapping case, the decrease of the distance may be, the rate of the decrease of the distance may be higher. So in the case of contraction mappings, we can reduce the distance of points in successive steps faster. Okay, this is what we want. So this is a very beneficial, very good property of mappings. So this is the reason why we want to have contraction mappings, because by placing restrictions on alpha, we can, in a way, we can determine the rate of the decrease of the distance between the successive steps, the distance between the points in successive steps. And contraction mapping, the use of contraction mappings in dynamic economics, especially in dynamic programming, is very extensive. So this is very good to have contraction mappings. Okay, the cases we had 4 cases: the Lipschitz condition, the non-expansive mapping, the contractive mapping, and the contraction mapping. And the restrictions became more and more rigorous in these cases. So of the 4 cases, contraction mapping, the conditions of contraction mappings are the harder. In all these cases, mappings are continuous. This is very important. This is a very important result, because the continuity of mappings is very essential. In all these cases, this is a sketch of the proof. In all these cases, we have continuous mappings, by which we mean that by decreasing the distance between x and y, we can decrease the distance between tx and ty. So continuity of mappings is interpreted in very similarly to the continuity of ordinary functions. So by reducing the distance between x and y, we must be able to reduce the distance between tx and ty, and it comes from the Lipschitz condition. If alpha is finite, which is supposed to be finite, then in all these cases we have continuous mappings. Okay, so now we have the most fundamental result. This is Banach's contraction principle. This is very general, but very important. We have a complete, most importantly, a complete metric space, such as a Banach space, and we have a contraction mapping on this space. According to Banach's contraction principle, then the mapping has a unique fixed point in the space, and most importantly, we can find it by iteration on the mapping. So in successive steps, we have the hope of finding the unique fixed point of the mapping. And most importantly, starting from any arbitrary point in the space. So Banach's contraction principle comes in various applications. So when we have, for instance, from the close end, an example from the close end, when we have a difference equation, then the conditions under which we can find the fixed point, the steady state of this difference equation. These conditions are based on Banach's contraction principle. So Banach's contraction principle is very fundamental, very important. The proof, we will skip the proof. It's not too demanding, but you can find it in the literature. The proof is based on showing that the mapping generates the Cauchy sequence, which must have a limit in a complete space, and we have a complete space. So if we have a sequence of points coming from successive steps of applying the operator, then this Cauchy sequence must have a limit point in the same space. And this limit point, which must exist, turns out to be the fixed point of the operator. And as an additional step, so the existence is demonstrated and the uniqueness is also demonstrated. So if we have a complete metric space and a contraction mapping, the mapping generates a Cauchy sequence that must have a limit in the same space, and this limit point turns out to be the fixed point of the mapping, which proves to be unique. From Banach's principle, we have two additional results. According to the first one, we can measure how we approach the fixed point of the operator in n successive steps. So if we start the iteration with the operator, the mapping, in arbitrary point x0, where x0 of course is in the space on which we interpret the operator, if we apply the operator in n successive steps, the distance between xn, the result of applying the operator in n successive steps, so the distance between xn and the fixed point of the operator is bounded. So we can measure, with this corollary, we can measure the rate of the convergence towards the fixed point. Another result from Banach's contraction principle, if we have a complete metric space, and in this complete metric space we have a closed subset, and if we have a mapping on this closed subset, then the mapping has a fixed point in this closed subset. So this is a very useful result, because when we have you can find related examples in the Stokey-Lucas textbook when we have the state space as a closed interval on the real line. So we can constrain the state space to a closed subset, a closed interval, on the real line. And in this case, if we have a mapping on this closed subset, then the mapping has a fixed point on this subset. The proof is not too complicated, and it is based on theorem 1 of Leuenberger that you can find on page 38 of the textbook. In a Banach space, this is just a sketch of the proof. In a Banach space, a subset is complete if and only if it is closed, and S is closed, so it must be complete. So actually, we repeat Banach's contraction principle. In a Banach space, in a complete metric space, we have a closed subset, which itself is a complete metric space. So if the mapping is on this closed metric space S, then we generate a Cauchy sequence in this complete metric space, and we must have a fixed point in this closed and complete metric space on the basis of Banach's contraction principle. Let's have an example. This is Leuenberger's example. This is an integral equation which defines an integral operator. So actually we have this is an operator which we apply to points in a function space. Function KTS is the kernel of the operator. Note that this integral operator is very similar to the Bellman operator in the stochastic case, which we extensively use in dynamic programming. The kernel is supposed to be in L2, so this is square integrable, and the square integral of the kernel of the operator is supposed to be finite. As Leuenberger claims, this integral operator defines a bounded linear operator. This is two claims, actually, bounded and linear operator on the space L2 with norm beta. Linearity is obvious. By linearity, we means that the operator is linear. This is obvious in the operator if you have a look at the operator, but boundedness must be demonstrated in a separate step. So first of all, what does it mean if we have a bounded operator? If we say an operator is bounded, then we are supposed to have a way to measure the operator. So we need an operator norm. In the next step, we will understand what operator norms mean. An operator norm is a specific norm which is defined on the space of operators. So operator norms, by operator norms we can measure norms, by which we mean that the maximum of how the given norm lengthens points in the space actually functions in a function space. So as we work on the space of functions, we have a function space, and with the operator we receive, by applying the operator to points in this function space, we receive functions belonging to the same vector space. So with the norm interpreted on this function space, we can measure the norm. We can calculate the norm of the point before, the function before and after the application of the operator. We will have two norms, and we can compare these norms. So we have a length of the function before the application, and we have a length after the application. We can compare these results, and we can see if there is a finite factor which can be interpreted as the maximum by which the operator lengthens the function, the point in this space. And by the norm of the operator, we understand this maximum factor. So this is the theory in very broad terms. This is the idea behind measuring norms. So, as Leuenberger claims, the integral operator, which is square integrable, and the integral is finite. So, according to Leuenberger's claim, the norm of the operator is a finite beta. And if it is true, and we will check it in the next step, if it is true, the image set of a bounded set is also bounded. So I think it requires no further explanation. If we have a bounded set of functions to which we apply the operator, which has finite norm, then the image set of this bounded set must also be finite. Okay, so let's check if the operator norm is really beta. The proof is a nice application of the Cauchy-Schwarz inequality, the importance of which can hardly be overstated. So let's take the opportunity to practice the application of the Cauchy-Schwarz inequality. First, let's be clear that the function x belongs to the same space as the function that we receive after the application of the operator. So we will move all along. We will move in the same vector space, function space L2, which is the space of square integrable functions. So we will do the same as I just explained. So we have a function x in the space L2, the function space L2. We apply the operator to the point, to the function. We receive a function in the same vector space. We will measure the length of this function, tx. We can calculate the norm because it belongs to the function space L2. And so we will try to measure the resulting function, and we will try to find a way to compare the length of this result to the norm, to the length of the initial function x. Okay, so this is what we are going to do. To be clear, as step 0, we just have a look at, let's have a look at the norm which we use. If we want to measure the operator with the norm, then we are supposed to perform this operation. This is a double integral at the end of the day, so we put the operator into the norm of the space L2. Okay, this is too much talking. So let's do this, and in the exercise we will see that linear operators on Banach spaces, bounded linear operators on Banach spaces, are also continuous. And we will also see that we can constrain lambda to have the operator as a contraction mapping. All right, so to find the norm of the operator, we should find the norm of the integral. So we try to calculate the norm of this integral, as I have just mentioned, which we can expand. So actually, this is the norm applied to something the operator. Okay, so we take the absolute value here. Please note that we take the absolute value of an integral which cannot be higher than the integral of the absolute value of the integrand. So we put the function into the absolute value and we take its norm. This is an important step because here we can realize that at this point we have s as the variable too. So here at this point we can use the Cauchy-Schwarz inequality in variable, this is important, in variable s. Okay, so up to now we have used the fact that the absolute value of an integral cannot be higher than the integral of the absolute value of the function. So, and as a next step, we will use the Cauchy-Schwarz inequality in variable s. Please note that this integral, according to the Cauchy-Schwarz inequality, cannot be higher than the norms of the two functions. So, in the next step, let's use this. The norm, which is still the same, and the norms of the functions. And the integral is with respect to t, but we used the Cauchy-Schwarz inequality in variable s. And given the fact that this norm is constant, this is a constant in variable t, because remember that we use the Cauchy-Schwarz inequality in s, so in t this is constant, so this whole guy equals this guy. This is the norm. And we have this guy as the integrand. And now let's expand the integrand. So we don't do anything but expanding what we have inside the integral, which is actually the norm, the square integral of functions. This is the norm in the space L2. And according to Luenberger's assumption, this integral is beta square. So this whole stuff equals beta times the norm of x. So finally, let's be very explicit. Finally, we have this claim. We have this result. It's more than a claim. It's now demonstrated. Okay, so yes. So the operator norm is beta. This is a very useful result. So we have demonstrated that the integral operator is bounded. As an additional result, additionally, in the case of linear operators on Banach spaces, boundedness implies continuity. Continuity for linear operators on Banach spaces. This is easy, so let's have a look at the proof. We have L as a bounded linear operator on X. We have X and Y as elements in the space, and age also in the space. Sorry, not Y. This is age. Sorry. I'm just confusing things. So this is not Y. This is age. So X and age in X, and age is non-zero. Okay. And now we have 2 points. So actually this guy is also in X. So we have 2 separate points in the space X. And by the linearity of the operator, we have this guy, which simply equals the norm of LH. And given the fact that this is bounded, there is a positive number m that satisfies this inequality. So if h tends to 0, if h tends to 0, then this left-hand side of the inequality tends to 0, and actually by the finite character of M, the right-hand side also tends towards 0. So the point is very familiar. By decreasing the distance between 2 points, and approaching 0, we can arbitrarily decrease the distance between the images of those 2 points. So boundedness, by which we mean that M is finite, we can ensure the continuity of the operator. So this is the reason why we say that the integral operator, the boundedness of the integral operator, implies continuity. So on these grounds, we can say the following. Let's apply the integral operator to two separate functions x and y in the same space. We can factor out lambda, and we apply the same operator to point y, and it equals, by the linearity of the integral operator, this guy. Please note that this function must belong to L2 because the space L2 is a Banach space, so it is closed with respect to linear combinations. So this function is in L2. And by our previous results, it follows that this inequality holds. Okay, so this is the point, and the other end is the point. So now we have this inequality. Let me highlight for emphasis. Let me highlight it for emphasis. Okay, and to have a contraction mapping, Leuenberger assumes that beta is positive. So to have a contraction mapping, this parameter is supposed to be less than 1. So if lambda is lower than 1 over beta, then it is a contraction mapping. So if we have, what we can see here is, I think it is very interesting. If we have a Lipschitz mapping, then we can constrain the constant parameter in this mapping to have a contraction mapping. And this is our restriction on the parameter of the mapping. Let's have a look at on Leuenberger's example from page 276. We have a differential equation in this form, and we are looking for the specific solution by which we can describe the dynamics of x. So let's think backwards. we need to find a function that we can differentiate with respect to t, and we receive this function. Actually, if we have this function, thinking backwards, this is a general constant c. If we have this function, we can differentiate it with respect to t, which is the upper threshold, upper limit of the integral. Then we will have, of course, the derivative of c is 0, so we will have this function. Now the only question regards the constant. So in time 0, no mistake, this is what I want to, sorry, then this is 0. So the constant is the initial value of the variable x. So actually, this is the specific solution of this differential equation. Okay, so we have the integral from this. We have the integral operator in this form. So by applying this integral operator to function x, we have another function in the same function space. Now, actually the space is the function of continuous functions with the max norm. With the max norm. So we can try to find the norm, this norm. Actually, this is the norm of this integral. And so this is the function space with the max norm. But so here we calculate the norm of the integral and this inequality holds. So if we put the function into the absolute value function, so if we take the absolute value of the difference of functions, then we receive this inequality. And note, the Lipschitz condition holds. This is an assumption. The Lipschitz condition holds, so we have this inequality. From which we have the following inequality because of the max norm of space C. Okay, and given that m is a constant and the norm of x1 minus x2 is also a constant, we can factor out this constant. And what remains is a very simple integral inside the norm. If we complete the integral between t and t0, then we have this expression, which cannot be higher. Note, we use the max norm, so the maximum of this expression is when t is t1, which is the upper limit of the interval. Okay, so t1 is that value of the variable that maximizes the expression. This is the upper threshold, upper limit of the interval. So finally, we have this expression. Actually, this is a mapping. This is a Lipschitz mapping. And if we want to make it a contraction mapping, then this inequality must hold, from which we have this inequality. Okay, let me go back to this stage, and let me highlight it, because very soon we will use this expression with exclamation marks. So we have this result, and on this ground, let's try to figure out how this mapping behaves. So first, n is 2. In this case, we have this norm. We will use the same steps. So we expand the norm, just like previously. But in the argument of f, now we have tx1 and tx2. Okay. This cannot be higher than the absolute value of the function, of the integrand. So we take the absolute value of the integrand, just like we did previously. The absolute value, d tau. Okay. And from the very same Lipschitz condition, we have that it cannot be higher than this guy coming from the Lipschitz condition. Okay, and because of the max norm, this cannot be higher than the norm of the difference, which is a function. Okay, and so we take the norm of a norm. And now we use that the norm of tx1 minus tx2 cannot be higher than this guy. Of course, it's m squared. And this is the point where we use this expression because we simply put it into the expression. Okay, and if we do the integral, okay, so we use this expression, yeah. If we complete the integral, we receive, let me highlight this expression because we are going to use it in the next step. And it cannot be higher. Note we use the max norm. So it's higher, is the highest when t is t1. So this is the case when n is 2. Proceeding with the same pattern, we use the previous results. Okay. Now we can take the absolute value. Now we use the Lipschitz condition. So after a few steps, let me skip them, we will have this line. And here we use this expression to say okay, and finally, if we do the integral, of which we will take the maximum, this is a pattern. This is supposed to be a pattern. Okay, and the maximum is where, again, where t is t1. Okay, so this is a pattern. This is a pattern. Which in general takes the shape factorial. That's all. This is what I wanted to show you. As a final example, let's have this integral operator. This is a very nice exercise to apply the Cauchy-Schwarz inequality to hone our skills in working with integral operators, which we extensively use in stochastic dynamic programming. So the space is the space, not C. X is a function in the space of L2 over the interval 0 and 2. So x is a square integrable function over the interval 0 and 2. On the basis of the norm, using the square is comfortable because we can get rid of the square root on the outside of the norm. And note that the integral operator is linear, so we have this function okay, and we can be sure that this function belongs to the same state space. Okay, it equals, so we take the norm. The norm is square integral. So we put the integral operator inside the absolute value. Note that this is an equation, function, sorry, in S. So the integral is with respect to S. So we can use the Cauchy-Schwarz inequality in the variable S after, sorry, something was missing here. So after realizing that by using the absolute value of the function, we might receive a higher value. Okay, so if we put the function into absolute value, then we might receive higher value. Okay, this square is useful because it drops the square root outside the norm. Okay, so now we have an integrand in absolute value, so Cauchy-Schwarz applies. Okay, so as the next step, we have this guy. The integrand is with respect to dt. This is the norm of x minus y. Actually, the square of the norm, because we eliminated the square root. And this is the norm of the other function. So this is the square of the norm of t minus s. And the whole stuff equals this double integral. One integral, two integral. This is known, so we have nothing to do with them. But this is something we need to find. So let's separate this problem into two integrals. And we integrate this expression with respect to s. According to the inside integral, after a few steps, which we skip now, we have this guy. Okay, you can do it by hand, so it's very nice. You can do it. You can do this by hand, and from this we can turn back to the outside integral with respect to t. Okay, let's skip the steps. This is 8/3. You can do this by hand. So finally, we have on the right hand side this expression. So altogether, taken all together, we have a Lipschitz mapping. Okay, from which it follows that we have a contraction mapping if lambda is not higher than 3/8. If this condition holds, this is a contraction mapping. So you can see that we can constrain mappings to be contractive. Sorry, not contractive, contraction mapping. this is what I wanted to show you. Okay, finally, let's try to find strategies, different strategies to find the fixed points of mappings. So far, we have studied cases where we placed restrictions on the mappings. So in Banach's contraction principle, if we have a complete space and a contraction mapping on the space, then the mapping has a fixed point. But to have a fixed point, the mapping must be a contraction mapping. Similar results can be found applicable to contractive mappings, and even in the case of continuous, very general continuous mappings, we can show the existence, if not the uniqueness, of fixed points. So this is one line of finding fixed points. There is another option. Instead of imposing properties, restrictions, assumptions on the mappings in order that they have fixed points, we can also place restrictions on the space on which we work. So we can impose topological structure, additional topological structure on the underlying space. So instead of restricting the mappings, we can restrict the space. And if we succeed, then a very loosely defined set of mappings will have fixed points on the proper spaces, on a proper space. So we need a useful definition to label this thing we are talking about. This label is the fixed point property. A metric space has the fixed point property if every continuous mapping, see, this is only continuous mapping. We don't need contractive or contraction mappings. We need continuous mappings. So if every continuous mapping, very general family of mappings, has a fixed point. At the most elementary level, we can easily show that any closed interval on the real line has the fixed point property. Just draw a square with the interval 0, 1 along the horizontal axis and 0, 1 along the vertical axis, and draw the diagonal, the 45-degree line from the left bottom to the right top. So we have the diagonal, and then try to draw a continuous line from the left to the right without crossing the diagonal. You cannot do this. So actually, the continuous line from the left to the right is the continuous mapping that maps the interval 0, 1 into the same interval along the vertical axis. And the point where your line crosses the diagonal, that is the fixed point. So in one way or another, you will cross the line, I mean the diagonal, with the graph of your mapping. So any closed interval along on the real line has the fixed point property. Brouwer extended this result in his fixed point theorem, according to which the closed unit ball around the origin in the n-dimension Euclidean space has the same fixed point property. And a further expansion proved the fixed point property for any non-empty compact and convex subsets of the n-dimension Euclidean space, or actually any finite dimensional normed linear space. So this was our introduction to the fixed point theorems. Thanks for watching.